Thank you. I'd like to thank the organizers for inviting me. It's a pleasure to speak at this conference. I didn't personally know Samuel, but everything I've heard about him makes me wish I had. And also, as you know, both a Mexican and an algebraic topologist, I think I'm automatically in his debt. So I want to talk to you about a space that you can associate to a topological group that in some sense tells you how far it is from being abelian. And so that space is denoted E com G. The first order of business will be defining this. But defining this will lead me to tell you first what B com G is. And to tell you that, I will have to remind you of a specific construction of the classifying space of a topological group. And so this isn't just the outline of the first few minutes of the talk, it's also a homotopy fiber sequence. Okay? So these spaces were first defined in a paper by Fred Cohen, Alejandro Adem, and Enrique Torres Giese, published in 2012. So they're young spaces. They're young spaces. All right, so let me remind you of a specific construction of BG. So here G is a topological group. And you can associate to it two topological categories, one which I will call calligraphic EG. This one has, maybe I should have written it. Let me give myself more space. So the space of objects here is G, and the space of morphisms is G cross G. And in this category, there is a unique morphism between any pair of objects. And there is another topological category I'll call calligraphic BG. Its space of objects is a single point, and the endomorphisms of that point is a copy of G. Composition is multiplication in G. There's a functor from EG to BG that sends the unique morphism from G to H to, well, it has to send it to some endomorphism of the unique object in BG, and it sends it precisely to H inverse G. Okay? And so if you take the nerve of these topological categories and the geometric realization, that's one specific construction of EG and BG. Okay, so for EG, you could take the geometric realization of the nerve of this topological category. You will get a map that's the geometric realization of that functor down to the nerve of this other topological category. Okay? And so what are in these simplicial spaces, the nerves of EG and BG, what are the n simplices? In general, the n simplices of the nerve of a category, well, you have to give n plus 1 objects and n morphisms between the consecutive pairs of objects, right? But in both of these categories, some of the data is uniquely determined and there's no point in writing it down, right? Here, all of the objects are the same, so there's no need to write the objects. So the nerves, the simplices here, they just, the data of one is just n different elements in the group, so this is G to the n, and the elements of the nerve here, the morphisms are unique, so there's no point in recording the morphisms, and you just need to keep track of the n plus 1 objects. All right? This is a classical, probably very well-known construction. And so the reason I want to talk about this specific construction of BG is that B com G will be defined as the geometric realization of sub-simplicial space of this nerve. Okay? So inside G to the n, you can look at the subspace of n tuples where all of the elements commute pairwise. Okay, and these subspaces form a subsimplicial space. Okay, and the realization of that is B com G. So let me, I don't know, maybe I'll denote this calligraphic B com G sub n, and then we will define. So then this simplicial space comes with a map to the nerve of BG and I'll define a simplicial space E com G simply as the preimage here of this subspace. Okay, so defined as a pullback, and then the spaces that I wanted to talk about are just the geometric realizations of these. All right. And it's this space, E com G, which I want you to think of as measuring how far G is from being abelian. And specifically, its homotopy type is supposed to measure how far G is from being abelian. You look at how far this is from being contractible. Okay? So in particular, all right. So notice that when G is abelian, then those commuting n tuples are all of the n tuples. B com G is the same as BG, and E com G is then contractible because it agrees with EG. Okay? All right, so before I get into how this measures how far from being abelian the group is, let me say a little bit about why you would want to study these. I think, well, so I only know what was published. I'm guessing at the history, and Fred can probably correct me. But so there's I mentioned the 2012 paper of Alejandro Adem, Fred Cohen, and Enrique Torres Giese. A few years earlier, Alejandro and Fred wrote another paper where they were looking at spaces of homomorphisms from discrete groups into Lie groups. And these spaces are more subtle than you might expect if you've never thought about them before. In particular, if your intuition comes from homotopy theory, here's one phenomenon you might find surprising. If you're a homotopy theorist, you're probably used to this fact. If you have a map between topological groups that is a homomorphism and is also a homotopy equivalence, then it induces a homotopy equivalence between the classifying spaces. Okay, so a homotopy theorist whose main interaction with groups is through their classifying space gets used to treating groups as only mattering up to homotopy equivalence. You can fix gamma and then look at the homomorphisms from gamma into two different groups, G and H, and the analogous property fails to hold. Okay, And it fails to hold even in an example that's not an arbitrary homomorphism, that's a homotopy equivalence, but one which you would really like for it to induce homotopy equivalences, the inclusion of the maximal compact subgroup of a Lie group. Okay, that's an example of, so if you have a Lie group, and K inside it, the maximal compact subgroup, in this case, the inclusion of K into G is a homomorphism that's a homotopy equivalence. It induces a homotopy equivalence between the classifying spaces, as I said, but it's possible for the induced map on spaces of homomorphisms to not be a homotopy equivalence. And in a strong sense, it can fail even to be surjective on connected components. Right, so there's no hope of it being a homotopy equivalence. There's an example in this paper of Alejandro and Fred's. One example is if you take the fundamental group of a surface of genus G, for G at least 2, and then you can take G to be SL2R, its maximal compact subgroup is abelian. Right? And in this example, they show that this is not even surjective on connected components. Okay? So those spaces are interesting. They're subtle, particularly if your intuition was trained by homotopy theory. And so one particular case that's of interest is looking at homomorphisms from Z to the n into G. This can be identified exactly with that space of n tuples where the elements commute pairwise by just looking at where the standard basis vectors go. And so once you notice that these assemble to form a simplicial space, then you probably want to know what happens when you realize the space, right? Fred showed us another example of that impulse on his talk on Monday, right? Once something assembles to form a simplicial space, you just have to realize it and see what you get. Okay, so maybe that's where these came from. Okay, so I'm trying to sell you on the idea that this ecom G measures, so the homotopy type of ecom G, how far it is from being contractible, measures how far G is from being commutative, right? So if you want to take this seriously as a measure of lack of commutativity, I guess the bare minimum requirement would be to prove that ecom G is contractible if and only if G is abelian. And you know, if this isn't true, we should probably just pack up, go home, and stop studying this. Unfortunately, it's not true. This fails, sadly. And I can show you a simple example. It's this one. If you take G to be SL2R, so this example of Alejandro and Fred's of a gamma for which the induced map here is not a homotopy equivalence is with the fundamental group of a surface. But if in place of that gamma you take Z to the n, there you do get a homotopy equivalence. And that's a consequence of a theorem of Alexandra Petit and Juan Suoto. Okay, so for this specific group, the map from here to here is an equivalence. So then this in turn forces the corresponding bcoms to be equivalences, to be equivalent, and ecom as a corollary of the fact that these are equivalences. And so since K is abelian, this one is contractible. Okay? So sadly, it doesn't satisfy the minimum requirements. Oh, okay, so maybe it's not a metric, it's a pseudo-metric. Doesn't mean, well, we didn't let it stop us, I guess. Lots of people work on this, and we don't mind that there is this counterexample. Maybe we should. But so, there are some cases, some classes of groups for which we can prove that. So, if G is either a compact, connected Lie group or discrete, then ecom G is contractible if and only if G is abelian. So in those classes, it's a good measure of lack of commutativity. And so I want to tell you briefly about this part right now, and then most of the talk I want to show you a very simple model for the homotopy type of ecom G as a simplicial complex. It's a nice simplicial complex that when G is a finite group is a finite simplicial complex. Finite simplicial complex you can even feed to a computer and it'll compute things about it for you. So let me first talk about this case. Notice that compact is necessary because of that counterexample over there. And so this is a report on work in progress with Bernardo Villarreal. We think that this should be true without connected, but haven't proved it yet. So maybe I'll say that's a conjecture. Is it a conjecture or a question? Conjecture. It's probably true, right? It's probably true. Okay. All right. So why does this happen? Well, there's some classical work from the 60s by Araki, James, and Thomas, I think. Yes. There's a paper from 1960 in which they show that a compact connected Lie group is homotopy abelian if and only if it is abelian. Homotopy abelian, there are several ways of defining it. I'll give you the definition that's most suited for our purpose. Homotopy abelian means that the commutator map is null. Okay? So if the commutator map is homotopic to a constant map, I'll call the group homotopy abelian. If the group is abelian, the commutator map is constant, right? Okay? So homotopy abelian just means it's homotopic to what it would be if it were abelian. And using this theorem, it's not too hard to show that ecom G is contractible if and only if the group is abelian. Let me just sketch that argument. Right. So when you have a simplicial space, you can, besides taking the geometric realization of the whole space, you can take a skeleton and take the geometric realization of the skeleton, and those filter the entire space. And here we're only going to need to look at the first skeleton. So the first skeleton of X, when you realize it, that's just realizing like the bottom part, X0 and X1 with the maps between them. And it's a fun little exercise, I guess, in category theory to say that an equivalent way of expressing this is you just take the homotopy pushout of the two face maps from 1 simplices to 0 simplices. So this is, if you look at 1 simplices to 0 simplices, the pushout of that, the homotopy pushout, gives you the geometric realization of the one skeleton. Okay? So you don't need to bother with the degeneracy and all that. It's just this homotopy pushout gives you the correct homotopy type. Okay. So, I mean, and the reason I called it an exercise in category theory is that all you have to do to check this is to show that the obvious functor from the diagram shape of the pushout to the diagram shape that gives you right, the functor that sends these two morphisms to D0 and D1, have to check that that's homotopy cofinal. Okay, it's a quick calculation. All right, so and you get a canonical map from this one skeleton to X. Okay, so I'm going to look at what this map. Wait, sorry, I am getting way ahead of myself, I think. Yeah, sorry. Okay, so we will eventually use this. The point is that, let me tell you right now what the one skeleton of E, G is. I guess this is calligraphic. So we will see that this is just G join G, eventually. And this is what we will use. So this has the homotopy type of the suspension here. And the conjugation map on G will, redefined to have this as its domain, will play a role. But so before I get to that, let me give you a description of what the space of simplices of E, G is. So remember, sadly I already erased it, but remember that the map that we had from the functor that we had from EG to BG involved just taking the difference of the endpoints of a morphism in EG, right? And so here the n simplices were G to the n plus 1, and we had a morphism here. The n simplices here are G to the n, and the map induced by the functor I described earlier will send an n plus 1 tuple to this n tuple. Okay? And we had defined the simplicial space E, G to just be the preimage under this map of the space of commuting n tuples. Okay? So that tells me that in the simplicial space E, G, the n simplices are given by n plus 1 tuples such that that n tuple on the bottom is commutative. Okay? So this is given by n plus 1 tuples such that all of these commute pairwise. Okay? All right, so this kind of relation will come up pretty often, and let me give it a name. I will say that a subset of a group G or even a sequence of elements. You can allow repetitions. It doesn't have to be a set. So this is affinely commutative. If that holds. If these commute pairwise. But there's many equivalent ways of saying this. Those commute. You can also take like a fixed one and consider all the differences with it. For example, and here the same. It's that these commute. That's equivalent. Another way to think about it is, for example, some elements commute if they are contained in some abelian subgroup, right? Some elements affinely commute if they're contained in a coset of an abelian subgroup. So if there exists G and A abelian with S contained in the coset, and notice here that I wrote a left coset. That corresponds to having the inverse on the left here. So maybe you could call this left affinely commutative, and there is a dual right version where this inverse goes on the other side, and here you would have a right coset. This is the one I'll use for now, but just be aware that the definition is asymmetric, and that's okay. All right. Okay, so then this ecom G is the simplicial space whose n simplices are n plus 1 tuples that affinely commute. Okay? Commute in the affine sense. Right? I mean, it's called affine commutativity because of this last equivalent condition. It means that they're in some translate. They're a translate of a commutative set. Okay? Does that make sense? Proving the equivalence here is very easy. So here, both of these involve some set of n n quotients between elements in the group, and those commute. When that happens, all of the quotients commute. So this is also equivalent to all of the quotients commuting. And you might wonder, well, here from just n of them commuting, I got all of them commuting. Here from a different collection of n of these commuting, I got that all of them commuting. How can I tell if I have some quotients that commute, if that's enough to get that they all commute? You just draw the graph connecting two elements when their quotient is in your commuting set, and then you will get that all of them commute if and only if that is a spanning set for the complete graph. Okay? So if it's a connected graph and it has all the vertices, then you get that this commutes. This is a path. This is a star-shaped graph. Okay? Does that make sense? So here we have 0 joined to all the others. In the first example here, we just have the path, 0 joined to 1, joined to 2, etc. I'm saying you can take any connected graph in place of those, and it would be equivalent. Okay? All right. So these are the n simplices of our simplicial space model for ecom G. And this lets you define an interesting simplicial map from here to the nerve of the commutator group. And it's defined by a formula that shouldn't work, but does exactly because of this definition. It's you send an n simplex to here. The n simplices here are collections of n elements of the commutator group, right? So I'll just take pairwise. I'll take the commutators of adjacent pairs. And your first instinct should probably be that there is no chance that this works, that this cannot define a simplicial map. But if you try to check it, you'll see that this condition is exactly what you need to make it work. Okay? So it's an improbable map. So, namely, you wouldn't expect the product of two commutators like this to be a single commutator. This seems unlikely, but it's true under this condition. Okay? So I really like this map because it seems unlikely. Okay. All right, so, sorry, I should have said all of this before I got into trying to explain the proof in the case of a compact connected Lie group of why there, if E, G is contractible, then G must be abelian. No, and this is going to rely on that theorem of Araki, James, and Thomas from 1960. Okay, so the idea is here we have a map of simplicial spaces. On the realization, we get an interesting map from E, G to BG. And there are a couple of people in the audience that have worked in this subject, E, G, B, G. If you want one thing from this talk, this map is interesting, and we don't know much about it. So if you want to look at that map, that would be great. Okay, and so here what I'm going to do is just see what this does on the first skeleton. Okay, on the first skeleton on both sides. So here, I'm going to look at the realization of the first skeleton, and the same here. And by naturality of the skeleton, we'll get a commuting square like this. And so we'll see that this commuting square winds up implying that if E, G is contractible, then G is homotopy abelian in that sense. And then the theorem will tell us that it has to be abelian. Okay? So let's see what these different things are. Remember the description I gave you for the one skeleton of a simplicial space. You just need to take the homotopy pushout of the level 1 with its two maps to level 0. So what do you get for the classifying space of a group? Well then, the one simplices are the group, the 0 simplices are a point, and then this here is the suspension of the group. Right? And should be clear from that homotopy pushout above. The one simplices is just the group, the 0 simplices is a point, you get the homotopy pushout that gives you the suspension. And here what do you get? So for E, G, the one simplices will be pairs of elements that affinely commute. But every pair of elements affinely commutes, because here there is only one thing that you want to commute, and one thing does commute. So here the one simplices is just G cross G. The 0 simplices are G, and the two maps are the projections. So this guy, let me do that here, is the homotopy pushout of the two projections. And as you probably know, the homotopy pushout of the two projections is the join. Okay? So here on this side we get the join. Now, as I mentioned earlier, the join has the homotopy type of the suspension of the smash, right? And so here, this top map, which is induced by the bottom map that I just defined, is some map from the suspension of G smash G to the suspension of the commutator. And looking at the definition of the bottom map, it's easy to convince yourself that it's actually just the commutator, okay? The commutator map that goes from G cross G to G, of course, has the property that if I take 1, comma anything, it goes to 1. And if I take anything, comma 1, it goes to 1. So that means that it descends to a map from the smash. And I'll call that the reduced commutator. Okay? And okay, so then it's not hard to convince yourself that this map here is just the suspension of the reduced commutator. Okay? By the way, this interesting map, I'll give it a name. Let's say calligraphic C. So we have this commuting square. Okay? And what I want to show is that if this space is contractible, then G is abelian, and my tool will be to show that it's homotopy abelian, right? So what does this tell you? If this space is contractible, that means that this composite is null, because it factors through a contractible space. So ecom G being contractible implies that this map, when you compose it all the way to the classifying space, is null. Okay? And then that's what you want, because the commutator factors through the adjoint of this map, right? The adjoint of this map would be some map from G smash G to loops on B G. If this composite is null, then its adjoint is also null. This is G, the commutator of G, which you can include in G, of course. And then, so if this map on the top is null, this map on the bottom is null, but this map is the reduced commutator. And if the reduced commutator is null, then this map is null. And so then the group is homotopy abelian, and the theorem tells us that G itself is abelian. Okay? So, so we were very lucky, because the one skeleton is the last skeleton that's easy. After this, it gets hard. Okay? All right, so now, let me see. I don't have very much time, but let me tell you about a model for ecom G in the case when G is discrete. So for the rest of the talk, G is now a discrete group. Which is the kind of thing that people in other fields of math just call a group. So in the case that G is a discrete group, we have a nice model that I'm going to call AFCOM G of ecom G as a simplicial complex. Okay, so this is a simplicial complex. With vertices, the elements of G, and simplices, the finite, affinely commutative subsets. Okay? And yeah, I guess all right. So this is a easy to describe simplicial complex. Its vertices are the elements of G, and some finite subset of G is a simplex if and only if those elements affinely commute, which means what's right there above, right? Means that the differences between them commute. Okay? And so if you look at the geometric realization of this simplicial complex, you get something that's homotopy equivalent to ecom G, but typically much smaller. Right? If G is a finite group, this is a finite dimensional simplicial complex. And ecom G, well, it has the homotopy type of one, but it's often infinite dimensional itself. Okay? And so at this point, this should not seem surprising at all, because ecom G is the geometric realization of a simplicial space where the n simplices are exactly the m plus 1 tuples that are affinely commutative. Okay? So you're probably familiar with the fact that that's one way to turn a simplicial complex into a simplicial set whose geometric realization has the same homotopy type. Okay, so let me call this, I don't know, it's a proposition, I guess. So if K is a simplicial complex, you can define a simplicial set, which I'll call the singular set of K. And its n simplices, this is exactly the way you turn a topological space into a simplicial set. You take for n simplices the space of maps, but here in the category of simplicial complexes, from the n simplex as a simplicial complex into K. So what does this actually mean? It means you get the space of n plus 1 tuples of vertices of K such that when you just ignore the order and look at the set of them, that forms a simplex. Ignore the order and the repetitions, and you get a simplex of K. Yep. Yeah, degenerate ones are the ones that have repeated vertices. Okay? And so here, the face maps are deleting vertices, the degeneracies are duplicating vertices. And it's exactly what you would expect. And then it's a fact that while this thing is usually very big, infinite dimensional, it does have the homotopy type of the geometric realization of K. Now, so when Bernardo Villarreal and I were thinking about this, we wanted a reference for this result. We both knew this was true. We didn't know a reference for it. We asked other people. Everybody knew it was true. Nobody knew a reference. So I decided to ask on MathOverflow for a reference. But it's tricky asking for references because I think it's basically because mathematicians love proving things and they don't really like giving references. So I was worried that if I asked a question there, I would get proofs instead of references. So I thought I will outsmart them all. I will first write a proof, and then when I ask the question, I will include the proof. And then when they see the question, they'll read the proof and say, oh, he already has a proof. Maybe when he says he wants a reference, that's literally what he means. I wasn't clever. This did not work. I have 2 more proofs, 0 references. Okay, so, but it's true, and everybody knows it's true, and lots of people can prove it. All right, so, and I could not outsmart MathOverflow. All right, so let me see how I'm doing for time. Maybe I should quickly sketch an alternative proof. Yeah, I think I should do that. Okay, so that folklore fact tells you this theorem over here, that the geometric realization of the simplicial complex does give you E, G. By the way, what's the idea behind all of the 3 proofs that I now know of this fact? It's the idea is simple. So you probably also know that if you pick an ordering on the vertices of the simplicial complex, and here you only take sequences that are non-decreasing for that order, then you get a different simplicial set whose geometric realization is homeomorphic to the geometric realization of K, right? Okay, so the ordered version, where in addition to this you also require that these respect some arbitrarily chosen total order on the vertices, this version gives you a different simplicial set whose realization is homeomorphic to the realization of K. So then you can ask, why is the one I wrote first homotopy equivalent to the one where you add this ordering condition? And basically, the ordered one is a colimit over the category of these tuples of simplices. For each one, you get a simplex. This gives you the ordered version of Sing. I'll write it Sing sub less than or equal. This is in the, well, just every simplicial set is the colimit of its simplices. And on the other hand, the the unordered version, you could write it as a colimit over the simplices of the ordered version. For each simplex in the ordered version, all you have to do is, besides just including one simplex, you have to include all the permutations of the vertices, right? So here, instead of taking the colimit of just a simplex for each simplex, I have to take the colimit of a space that has, that instead of the simplex consists of all sequences, not just the ordered sequences. And I'll call that En, I guess, right? So this En, you can think of it as the realization of the nerve of the discrete category on n+1 objects, okay? And so then why are these two things homotopy equivalent? Well, this is contractible and this is also contractible. So if you just show that each of these is a homotopy colimit, then they have to be equivalent, right? They're both equivalent to just the shape of the category of simplices in the ordered version, all right? And all the proofs are basically versions of that, I think. All right. Okay, so let's see. Let me now quickly mention a different proof of the fact that the geometric realization of that simplicial complex is ecom G. Okay? So first, so remember that G is a discrete group. Here, this bcom G, so remember this was the geometric realization of the simplicial set. It's a set because G is discrete. The simplicial set of commuting n-tuples, right? Each commuting n-tuple lies in some abelian group. So this is just the union of all the classifying spaces of abelian groups. Okay? And so now the class of all abelian subgroups of G is ordered by inclusion, and you can check then that, you know, since when it's closed under intersections, the intersection of two abelian subgroups is again an abelian subgroup, this union is just the colimit. It's the colimit indexed by this partially ordered set of abelian subgroups. And again, because we're including all intersections, it's not too hard to check that that is the homotopy colimit. And now as people who know me know very well, my favorite trick in the world is to use that homotopy colimits are universal. Homotopy pullback across any morphism, any function, will take a homotopy colimit to another homotopy colimit. And it's one of my favorite facts in the sense that if there's anything that's a simple consequence of that and I don't realize it's a simple consequence of that, I feel shame. And this means that we can say that ecom G is the homotopy colimit of the pullbacks. So by its very definition as a pullback, bcom G is just the homotopy, sorry, ecom G is the homotopy fiber of the map from bcom G to bg. So this is the homotopy colimit of those homotopy fibers. Right? And those homotopy fibers are just discrete sets. They're the set of cosets. Right? So this is the homotopy colimit of the set of cosets. And one model for a homotopy colimit of discrete sets is just the is given by the Grothendieck construction. Okay, so this G mod something is a functor from the poset of abelian cosets of G to sets. I want to take I regard these as discrete spaces. I want to take the homotopy colimit. One model is given by the Groton deconstruction of this functor, right? And it's not too hard to check that the Groton deconstruction of this functor, so let's see, what is it? It's a category whose objects are elements of these sets. So it's a category whose objects are cosets of abelian subgroups. It just turns out to be the partial order of cosets of abelian subgroups ordered by inclusion. So this Groton deconstruction is isomorphic, in fact, to, I'll call it ab-co. So this is the poset of cosets of abelian subgroups of G. Okay? So already I'm giving you a nice alternative model for the homotopy type of ecom G. It's often nice to have a space given as the geometric realization of the nerve of a poset if the definition of the poset is nice and simple. So this is the nerve of this poset of abelian cosets. Okay? All right, so now let's look at a cover of this poset by subposets. Right? So for every element in the group, let me look at just the subposet of all abelian cosets that contain that element. So I can write it this way. If a coset contains the element G, then it is the coset of G, right? So this is a family of subposets of the poset of cosets, which is very fun to say. And it has, let's see what the intersection pattern that they have is. So first of all, maybe even before the intersection pattern, let me just point out that that poset is contractible. It has the smallest element, right? G of the trivial group is the smallest element. And if you have a poset with the smallest element, its nerve is contractible. You can contract it all towards the smallest element. Okay, so how do these things intersect? It's easy to figure out. So when do these intersect? They intersect when there is a single abelian coset that contains all of these elements, right? That's the case in which if that doesn't happen, they don't intersect. So right off the bat, the intersection is empty if this set does not commute affinely. If this is not affinely commutative. Now, if it is affinely commutative, there is a single abelian coset that contains all of them, and the smallest such is, of course, the abelian coset of the group generated by the differences, right? So when it's not empty, it's contractible because it's again a poset that has a minimal element. So here you get something contractible if this is affinely commutative. And the reason it's contractible is that it has a smallest element namely the coset of the subgroup generated by the differences. Right? Okay. So this is the subgroup generated by all the pairwise differences. And if this collection is affinely commutative, this is an abelian subgroup, and it's contained in any coset of an abelian subgroup that contains all of these elements. Okay? So these have a nice intersection pattern. An intersection of finitely many of them is either empty or contractible, right? And then the nerve theorem is exactly about the situation. The nerve theorem says that if you have a complex, and you have a cover by subcomplexes with this feature that the intersection of a bunch of them is always either empty or contractible, then the complex that you had has the same homotopy type as, so this part we already knew, the nerve theorem tells us that this has the same homotopy type as a simplicial complex that records when the intersections are non-empty, right? But what is that simplicial complex? It has simplices precisely when the subset is affinely commutative. So the nerve theorem tells us that this is affine AFCOM of G. Okay? Right, so I don't know. I guess the folklore theorem before makes this proof obsolete, but I'm fond of this proof. Okay, so let me see. I am probably just about out of time. Let me just mention very briefly one last thing. Oh, I definitely should mention briefly one last thing because I have not yet proved that when G is discrete, E, G is contractible only if and only if G is abelian, right? And we can do one better for G discrete. E, G is contractible if and only if it's simply connected. This is not true for non-discrete. If and only if G is abelian. Now that we have this simplicial complex, whenever you have a simplicial complex, there is a very nice presentation of the fundamental group. It has generators corresponding to all one simplices. And here, the one simplices are just in bijection with all pairs of elements, right? Any pair of elements is affinely commutative, so you just get one generator for every pair of elements. And these are subject to the following relations. Just so that I don't have to write special cases, let me include here the diagonal ones, but those are the identity. And so that I don't have to worry about picking an order, let me just include all orders, but they're inverse to each other. And then the interesting relation comes from the triangles. When you have a connected simplicial complex, the fundamental group has one generator for each edge, and it has one relation for each triangle that says the path going along one edge and then the other edge is the same as going along the third edge. So that relation just says that xgh times xhk equals xgk whenever these three commute affinely. Okay? So that's a very convenient presentation for the fundamental group. And the earlier map that I had defined that goes, so remember that I told you there was this interesting map to, my calligraphics are terrible, to the classifying space of the commutator group. I can tell you what it does on pi 1. And so on pi 1, it'll be a map from the group with the presentation that I wrote above to the commutator group. And if you trace through the definitions, or otherwise you could just guess, it's the one that sends the generators to this. And so those first relations are trivial. The last one is the one I said you should not expect, but it holds precisely because of affine commutativity, right? So here I have a group homomorphism to the commutator group, which is clearly surjective because I'm hitting all the generators of the commutator subgroup. This map is surjective, right? So that means that it's always surjective. So if this is trivial, then the commutator must be trivial and the group must be abelian. Okay? All right. I think I'll stop there. Thank you.
Questions, please?
Yeah.
First of all, Omar, I really loved your talk. It was very nice and very transparent.
Thank you.
I do have a little question, which is the way you chose to work, which you convince me is the correct approach. But there is another model that I would use for ecom-G.
Oh, right, yeah, yeah.
Namely, you can take the simplicity reduction.
I'll write it down so that you don't have to say it.
Right, exactly.
Yeah, it's this one.
Exactly. So at each level,
It's isomorphic.
It's isomorphic to the one you use.
Yeah, and the isomorphism is easy enough. So here you have like one weird element and then a bunch of elements that commute. In the model that I prefer, you would just send this to GH1, GH2. What do I want? I want the quotients to recover this. This map is unimprovisable. It's this or something very closely related to this.
Exactly. So what I cannot work out in my head is this simplicial space that you're constructing through this point of view, what does that correspond to? I mean,
it's isomorphic to your simplicial
exactly,
space. It's not.
It's not very transparent. I thought you knew the answer. Definitely, this is the way to. Your approach is definitely the approach.
Right. So I think of it this way. We've had many philosophical conversations about this, Bernardo and I. And so first of all, it's isomorphic. So there's not much point in discussing the difference. But secondly, it's just so these are the nerves of a category. An n-simplex in the nerve of a category really is n plus 1 objects together with n morphisms between consecutive pairs. And remembering this or remembering that is just different encodings, right? So if you have an n-simplex in that thing, you can record its starting point and you can record the jumps it makes. Right? These are labeled by the morphism in BG that they get sent to. Okay? So one way to specify the n-simplex is to give the starting point and to give the length of the jumps. An alternative way is to record all of the objects. Right? It's just the same. There are two different ways to record the data of an n-simplex, and I would argue that neither one is the correct one. The correct one just has all of the information.
Say anything about the local system or the map of BCOM, G, and BG?
We've tried looking at it in a few cases. No, I think the answer is we can't say anything, but we're trying to. We can't say anything about it, but we're trying to. I mean, I could tell you what it is for SU2 or for or O2, but that's about it. Yeah, and for discrete groups, we haven't really calculated it yet in any examples. So we're looking at it. We don't have anything to say yet.
Other questions?
Yeah.
So is there an angle of these affine commutative sets in each case?
Sorry, could you repeat that?
So you have these affine commutative sets
Mm-hmm.
in discrete case. What would be the angle of the each case?
Well, it's the simplicial space whose n-simplices are affinely commuting n plus 1 tuples. I mean, the first version I talked about, that is the continuous version. You can't get away with making it a simplicial complex. You have to make it a simplicial space, but it's exactly the same flavor of simplicial thing.
What if you just run the same argument for a different case?
Oh, this argument about the nerve?
Right.
You get a topological category, I think.
Yeah, you would need a version of the nerve theorem for like covers with topology. Like the cover is indexed by a topological space. I don't know of any such version. Yeah.
No questions? No more questions.
All right.
Well, then let's
Thank you.
thank Omar. Muy bonito.